Let's see what we mean by this. Let's assume the operating system manages two processes, P1 and P2. It has already created them, and they're process control blocks, and these process control blocks are stored somewhere in memory. Let's say P1 is currently running on the CPU, and P2 is idle. What this means that P1 is running is that the CPU registers currently hold the values that correspond to the state of P1. So they will ultimately need to be stored in PCB of P1. Then at some point, the operating system decides to interrupt P1, so P1 will become idle. Now, what the operating system has to do, it has to save all the state information regarding P1, including the CPU registers, into the process control block for P1. Next, the operating system must restore the state about process 2 so that process 2 can execute. What that means is that it has to update the CPU registers with values that correspond to those of the program control block for process 2. If at some point during its execution, P2 needs more physical memory, it will make a request via the malloc call, for instance, and the operating system will allocate that memory and establish new virtual to physical address mappings for P2 and update as appropriate the control block data structure for process P2. When P2 is done executing, or when the operating system decides to interrupt P2, it will save all of the information regarding P2 state in the process control block for P2, and then it will restore the process control block for P1. P1 will now be running, and the CPU registers will reflect the state of P1. Given that the value of the process control block for P1 corresponds exactly to the values it had when we interrupted P1 earlier, that means that P1 will resume its execution at the exact same point where it was interrupted earlier by the operating system. Each time the swapping between processes is performed, the operating system performs what we call context switch.